Yeah, thanks for the invitation, Florian and George. I would like to talk about new estimators for directional data. This is joint work with Robert Gorn from Manchester and Yvick Swan from Brussels. And we call these new point estimators Stein estimators because they're based on so-called Stein operators from an area which is called Stein's method. And with these operators, we can characterize probability distributions in the following sense. So we call an operator A, theta, a Stein operator for probability distribution, p theta, where theta is the parameter of interest, the one which we want to estimate out of an parameter space, which is p-dimensional in this case. And we call A an Stein operator if the expectation of A applied to some test function f of x is 0 if x follows the probability distribution p theta for all functions f belonging to a certain class of functions. And if this function f is large enough, the Stein operator, together with this class of functions, capital F, actually characterizes the probability distribution p. And now how do we want to use the Stein operator for an estimation of the parameter theta? Well, let's say we have an IID sample, x1 to xn, distributed according to p theta. Then we choose as many test functions as we have unknown parameters, in this case, p test functions, f1 to fp, out of this function class. And we apply the Stein operator to each of those test functions. We replace the mean by the empirical sample mean. And then we end up with p of these equations here. And these we just solve for theta. So it's very easy. It's basically just moment estimation, what's happening here. Before moving to directional distributions, let's look at easy univariate. Let's look at the univariate case. So for univariate probability distributions, we often use the so-called density approach in order to obtain such a Stein operator. So if we know that our target distribution has a differentiable PDF p theta, we know that the Stein operator is simply given through this expression here. Gradient of p times some additional function tau times test function divided by p. And the test functions, the class of functions consist of all functions that are differentiable and such that f times p times tau vanishes on the boundary of the support of the distribution. And one may note here that possibly a complicated normalizing constant will just disappear because we have derivative of p over p, right? This function tau is just there to add some flexibility in order to gain a simple Stein operator. And for univariate distributions, it is often convenient to consider the so-called Stein kernel for the function tau. The Stein kernel is defined like that, where x just follows the distribution p. And why is that a good choice? Well, if we choose tau like that, the Stein operator just simplifies to this expression here. So quite simple, we have tau appearing again, and then just the expectation of x. And in fact, this Stein kernel here is polynomial for each member of the Pearson family. So already for quite wide class of distributions, we get a simple Stein operator. Let's probably look at a very concrete example in order to get like a feeling how this works. So the univariate normal distribution. So very easy. The normal distribution depends on two parameters, the mean and the variance. And with the density approach, we can get a Stein operator, which the very well-known Stein operator for the normal distribution, which looks like this. And now, since we have two parameters to estimate, mu and sigma squared, we choose two test functions, f1 and f2, and we arrive at these two equations. which is just a system of linear equations in the parameters in mu and sigma squared, which we can solve explicitly for any two test functions f1 and f2. And thus, for any choice of test functions, we get a different estimator for mu and sigma squared. Certainly under some technical assumptions on f1 and f2. And for example, if we choose as f1 the constant function and as f2 the identity, we get the standard estimators for the normal distribution. So to sum up what we have for probability distributions in Euclidean space. So we know that these estimators exist with probability converging to 1 as the sample size grows, and we know that they are strongly consistent under weak assumptions. We also can show, as it is standard for moment type estimators, that they're asymptotically normal, and the covariance matrix can be worked out in terms of the test functions. It is also possible to extend this approach to a strictly stationary and ergodic time series, but only for the estimation of marginal parameters. So we cannot estimate any parameters that would describe the dependency structure of the time series. And also, we know, like in the univariate case, we know how to choose these test functions in an optimal way, which would give asymptotic efficiency. And we look at a lot of examples, standard examples like gamma, beta, and the Nakagami distribution. A little more interesting, the exponential polynomial models, because here for a high dimension of the parameter space, MLE and standard moment estimation can already be a little bit tricky. And we get, with our approach, we get explicit estimators for any dimension of the parameter space. And we also looked at truncated distribution. One example is a truncated multivariate normal distribution, where we also get explicit estimators for any piecewise smooth truncation domain. The nice thing with these truncated distributions is as well that usually the difficulty there is the normalizing constant, which just disappears in our case, right? So this works out quite well. But yeah, today we want to focus rather on data on manifolds. So how does that work on manifolds? Regarding the Stein operator, it works as follows. So let M be a smooth compact manifold. And then this here is just Green's identity. Here we have the Laplace-Beltrami operator, the gradient on the manifold, and the Riemannian metric. Yeah? And U and V are just smooth functions on M. And one knows that for a manifold without boundary, so for example, the sphere, this right-hand side here will just be 0, will just disappear. And so if we choose now U as the density on M, P theta, again, depending on some parameter of interest, and V as a test function, then we obtain the following Stein operator. This is basically just the left-hand side from Green's identity. Note that we have to pull out one time the density because we take the expectation, right? That's why we have an additional density here in the denominator. And then we do exactly the same stuff. So this just reduces to the well-known Langevin Stein operator in Euclidean space. And as before, for a given sample x1 to xn, following the probability distribution with PDF p theta, we just replace the expectation by the sample mean and resolve the empirical equivalent of the Stein identity for the unknown parameter. And our main focus will be on the Fischer-Bingham distribution. The Fischer-Bingham distribution depends on two parameters, mu and a. Mu is a vector and a is a symmetric matrix. And it has this density. And when it comes to parameter estimation for the Fischer-Bingham distribution, then maximum likelihood estimation has been considered several times in the literature. But there are mainly two challenges with MLE here. At first, if you have a very large, if D is large, if the dimension is very high, then you just end up with a high dimensional optimization problem, which you would have to solve numerically. And so you might not find the global maximum, right? And the other challenge is that the normalizing constant of this probability distribution, as well for high dimension, is quite difficult to estimate. So it's computationally very heavy and numerically not very stable. So as a consequence, MLE just is very complicated. So for example, there are several works in the literature only dedicated to the estimation of the normalizing constant for the Fischer-Bingham distribution. Now, how does that look like with our approach? When you look at the spherical Stein operator, then there are mainly these two expressions appearing: the spherical Laplace-Beltrami operator and this guy here, involving the spherical Riemannian metric and the spherical gradient. And it is very well known that you can express both of these quantities in terms of their Euclidean counterparts. So here, these are just the Euclidean operators, Euclidean Hessian, gradient, and Laplace operators. And therefore, if we now also note that the density, the PDF of the Fischer-Bingham distribution, is actually a very easy function when you look at it as a function defined on RD, right? It's just an exponential function, and these two guys here, not very difficult. And therefore, our resulting Stein operator is not very complicated. It's just that, involving the spherical Laplacian, and this is also quite easy. This is just the Euclidean gradient. And now we do the exact same thing as before. We want to estimate mu and A given a sample. And therefore, we choose two functions, one vector-valued function for mu and one matrix-valued function for the matrix A. And then we end up with a set of equations. We again look at the empirical sample mean, and we try to solve this for theta, which is in this case mu and A. And as it turns out, you can solve that completely explicitly. You don't have to read all that in detail here. This is just to show you that the estimators are completely explicit. So the bar here just means sample mean. Bold D is the duplication matrix. And for any two test functions, F1 and F2, you get you can solve this explicitly, and you get these two estimators here, A hat and mu hat. Okay. This is just to show you that the Fischer-Bingham distribution is a very flexible distribution on the sphere. So this is for like on the two-dimensional sphere for different parameter constellations. The Fischer-Bingham distribution just can admit very different shapes on the sphere, as you can see here. So it's quite flexible. We found the following choice of test functions quite convenient. So we chose the identity, and for the matrix-valued function x times x transpose. And then we conducted a simulation study for different parameter constellations and in different columns here. And here you find simulation results for our Stein estimators that you saw on the previous slide, mu hat and A hat. Here are the MSEs for mu with respect to the Euclidean distance, with A with respect to the spectral norm. For sample size 1,000 and 1,000 Monte Carlo repetitions, the third row here is reports the relative frequency of how many computational failures we encountered during the simulation study. And as you can see, there were no problems. Like the estimators always existed, no problems with the calculations. And so we couldn't add any other estimators to compare with, because there are several works for MLE, but and we implemented them, but they turned out to depend heavily on several initial parameters that one has to set, and also on the starting point of the numerical procedure in order to calculate the MLE. So we didn't really feel comfortable of including them in the simulation study, and so we end up with just these results here. I mean, they look somewhat small to me. But yeah, unfortunately, no other estimators to compare with. What we did note are like quite high values here especially in the first column. And then we investigated that a little bit further. And as it turns out, there is some kind of parameter identification problem. So in order to clarify that. So when we generated a sample with size 1000 with the parameter values mu 4000 and a just the zero matrix, then we got the following results for our Stein estimator. So these are the two estimates, and you see those are very different than the true parameters. So they would result in very large values for the respective MSEs. But if you plot because this is just in 3 dimensions, right? So you can plot the two distributions with the original parameters and with the estimated ones, and as it turns out, they are very similar. So there's some kind of in theory the parameters are completely identifiable, but in practice you can have very different parameter constellations that would produce almost the same shape on the sphere for the Fischer-Bingham distribution. So this is a bit of a problem when it comes to evaluation of the estimators. Okay, so far so good about the Fischer-Bingham distribution. We also looked at a very famous subclass, namely the von Mises-Fischer distribution, which is the spherical equivalent of the normal distribution in Euclidean space. Depends on 2 parameters, mu and kappa, and this is the density. And yeah, here we can do the same thing. We chose the following approach. So we chose a vector value test function. And then since we're gonna estimate mu with the directional sample mean, just a standard estimator for mu, we're only left with estimation of the concentration parameter kappa. And since we end up with D equations here, but only have a univariate parameter to estimate, we followed some least squares type approach, right? And we end up with this estimator kappa hat, where Kn and Qn are defined right here for any test function f. And we found the choice f of x equals x as very convenient, and this results in the following estimator for kappa. A mu hat here is the directional sample mean. And this is now a kind of proof of concept, because parameter estimation for the von Mises-Fischer is straightforward. MLE, you need to solve it numerically, but it's usually quite stable. And there are also very good explicit approximations of the MLE. So this is kind of proof of concept in cases where we can compare our approach to other methods. How good are we in comparison to, for example, the asymptotically efficient MLE? And so we once again conducted the Monte Carlo simulation study. And here are the results. Here we have only for kappa, right? Because mu, the directional mean, is estimated in the same way for all estimation methods. Here we computed bias and MSE for different dimensions and different values of kappa. And the best result is highlighted. And as it turns out, the Stein estimator performs quite well. So here we compare to the MLE in the first column, and the second column, the score matching approach has lately been generalized to spherical distributions. So we also compare to that one, because they also get rid of the normalizing constant. And yeah, the Stein estimator is outperforming for throughout all parameter constellations, and also in terms of MSE performs very well, very close to the MLE. And sometimes
you have roughly 1 more minute.
Yes, thanks. I'm almost done. And yeah, we're quite satisfied with these results. This is for sample size 100. And yeah, we can also calculate the asymptotic norm and the asymptotic covariance of our sign estimator. The result is given here. And then you can also, of course, compare to the inverse of the Fischer information, the asymptotic covariance of the MLE. And the sign estimator is, of course, not exactly asymptotically efficient, but very, very close. So if you plot it, you almost don't see a difference between the curves if you plot it depending on the true parameter kappa. And so there's if you're interested, there's a paper on arXiv. There we also look at the real data example from machine learning, because the Fisher-Bingham distribution has been lately used as a distribution on the latent space for autoencoders. And here we apply this estimator to an autoencoder. But I unfortunately won't have time to talk about that anymore. And then I already want to thank you for your attention.